So this lesson is going to be about Newton's second law. The learning target for this lesson is I understand how mass affects an object's acceleration. We've got to be able to make calculations using Newton's second law as well. And so if we think about these two objects here, these two vehicles, we want to, which one would accelerate more? If I had the same force acting on both of them, let's say it's kind of unrealistic, but if I had the semi that had the same force as the car, and we think about which one is going to accelerate more, we know that the only difference, as long as they have the same force, right, the only difference between them is the mass. And so we know that the car is going to accelerate more than the truck does. And so this one has a higher mass and has less acceleration, right? And if I have something that has less mass, we have greater acceleration. And this is kind of similar to inertia, right? We know that the semi has more inertia because it has more mass, and so it's going to be harder to change the motion of the semi, and so it's going to accelerate less. Let's say I took this car, right, and I didn't do anything with the mass. I kept it the same mass, but now what if I put a bigger engine in it, and now all of a sudden I increase the force that engine can put out. And so this car is the same mass, but it's being acted on by more force. I know that the acceleration is going to go up in this situation because we're getting more power, more force accelerating this car, and the mass didn't change at all. So we know that if I push something harder, it's going to have a bigger change in motion. And so the relationships between mass and acceleration and force and acceleration is really all about, is what Newton's second law is all about. So just to state this out there, how do force and mass affect acceleration? If I have a greater force, I get a greater acceleration. And the opposite would also be true. If I had less force, I'd have less acceleration. I have less pushing that. And if I have a greater mass, I have less acceleration. Because this thing has more inertia, so it's going to be harder to move. And so I can see that as force and acceleration are directly related to each other, as one increases, the other increases, and mass and acceleration are inversely related to each other. As mass increases, acceleration drops. And so this is what the basis for Newton's second law is going to be. And really what we're going to be doing here is we're going to be putting numbers to this relationship. And so as we look at Newton's second law, I have the equation triangle here that we're going to use to get our equations for Newton's second law. And you can see that acceleration is on here, measured in meters per second squared. And it's really important that we know what these units are for these different variables. And we saw that forces is here, and it's measured in newtons. And I can see that mass is measured in kilograms. And so as I am trying to find some of these variables in problems, so let's say I knew what the force on something was, I knew what the mass of it was, and I want to know how much it's going to accelerate. So if I was looking for acceleration, remember with my equation triangle, I cover up my A, I'm left with force divided by mass. And so my equation here is force divided by mass. Right, now if I was going to look for, let's say I had the force acting on something, and I knew how it was accelerating, and I was looking for its mass. So I cover up my mass on my equation triangle, and I'm left with force divided by acceleration. Right. And then the last one here, if I was just trying to find the force that something was acting with, let's say I knew how fast a car was accelerating, I knew how much mass it had, and I wanted to figure out how much force is this engine putting out. And so I was looking for force. Remember, I cover up the one that I'm looking for. I have mass times acceleration. Mass times acceleration. So that's my equation. I can find my force measured in newtons with that equation. And so we're going to be using these equations in the following problems to solve for some of these variables. So this problem right here, a 24 Newton force acts on an 8 kilogram rock. What is the rock's acceleration? So I'm looking through my problem and I see that I am looking for acceleration. And so I am looking for this and I'm trying to get my equation. So I cover up acceleration. I'm left force divided by my mass. And so I copy that down right here. Now I look at my problem because I need to find the force, and I can see that this says 24 Newton force, and so I know that that's my force. I see 8 kilograms, and I know that kilograms measures mass, and so there's my mass. And so now I can plug in for my 24 newtons divided by my 8 kilograms, and I'm left with an acceleration of 3 meters per second squared. And it's really important that I remember that 3 meters, or that meters per second squared, is my units for acceleration here. But that would be the answer for this problem. And so this problem here, if I had 30 Newton force acting on a skater caused an acceleration of 0.6 meters per second squared, what is the mass of the skater? So I am looking for mass. And so I start with m equals, I look for it in my equation triangle and cover it up, and I'm left with force divided by acceleration. And so that's my equation here. Right, so now I go looking at my problem and I try to find my force, which I see right here because it says 30 newtons, which I know is how force is measured. And I see my acceleration in meters per second squared, and so I know that 0.6 is my acceleration. And so now I can plug these in to my equation. 30 newtons divided by 0.6 meters per second squared. And I get a mass that equals, this would be 50 kilograms. And I know that mass is measured in kilograms, and so I can put that label behind my 50. And so this would be the answer to this problem. So my last problem here. What net force on a 14 kilogram wagon would produce an acceleration of 1.5 meters per second squared? So I start by looking for what I'm trying to find here. I'm trying to find the net force. What net force would be caused by this? So I look for my net force, cross it out, and I'm left with mass times acceleration. And so I know that force equals mass times acceleration. So I go looking through my problem to try to find my mass, which I find here with 14 kilograms because I know that kilograms is how mass is measured. And then I look for my acceleration, which I find here because I know that meters per second squared is how acceleration is measured. And it says acceleration right here. So I can also look at that. I plug in for my problem here, and I see 14 kilograms times an acceleration of 1.5 meters per second squared. And I end up with F equals 21, and I know that the units for forces are in newtons, and so I add that to the end of my problem. My problem is 21 newtons is the force acting on this wagon. And so the goal of this lesson was for you to understand the relationship between mass and force and acceleration. Remember that if mass goes up, the acceleration goes down because we have more inertia, and if the force goes up, we're pushing it harder, and so acceleration is going to be greater. And then to be able to use this equation triangle and be able to use the equation of Newton's second laws to solve these problems. If you're looking for kind of a generic, easy to remember equation, you can use the force equals mass times acceleration. That's usually how you'll see Newton's second law. And then from there you can figure out my force goes up top here, and since my mass and acceleration are multiplied by each other, they go at the bottom, and then you can set up your equation triangle. Or you can always do the algebra moving things around. You know, if I was looking for mass, I'd divide both sides by A, and I'd be left with m equals F divided by A. You can also do it that way. But I hope this lesson's helped you to understand Newton's second law and how to calculate out the force, the mass, and the acceleration of an object.